Welcome in this tutorial for midasNFX. So we'll talk about the analysis of this clip. So this is nonlinear static analysis, and we'll see how to simulate the displacement of the clip inside this. So how to assign the contacts and the displacement conditions. So let's go into the software. So you see I already imported my model. So this is a CAD model imported from Parasolid format. And now I can begin to do the modeling. So what I'll be doing is follow the steps that need to be done in order to do this analysis. So the first step will be to to assign, let's say, the material and the material properties. Then I will create the mesh, a very important step, especially in this contact zone. And then I will assign the boundary conditions. So I will fix this model, I will assign the displacement, and I will create the analysis case and just show you the analysis results. So let's begin. So the first step, as I was telling, is to assign the material properties. So here I have already alloy steel, which is assigned by default, but I can choose any material in the material database, so I'll just keep it with that. Now I have to create a property which will be related to this. So I'll choose a 3D property, solid, and click on OK, and I made a solid property, so it's easy. Now the second step is the meshing. So when I want to do the meshing, there's a bit of tricky part is that there will be a contact in this zone. So the importance, there's a very high importance of the quality of the mesh around this zone and this zone, so the two parts which are coming into contact. So to be sure that I will have this kind of precision, there's several methods. So the first method I'll use is just to assign size control over the boundary condition. So you see that I select these edges here, and I will just select a precise size. So let's take a look. If I choose 1 millimeter, I use the preview, it will give me a mesh which will be around this size, so it looks okay. So I just choose apply, and now I'll do the same for these edges. So I just select these edges and I will apply same size of 1 millimeter on these edges. Now if I measure that, you see that there's no constraint on the thickness, so probably there will be one mesh on the thickness, so this is a bit too low. So in order to get a good contact condition, I need to have a minimum 3 mesh in the thickness. So again, I just use this same edge contact, so I select the edges here, so the 3 edges, and yeah, these edges, this one, this one, this one, and let's say this one, okay. And then I use the number of division, and let's input the minimum 3, let's put okay. So this will help me to control the size on these parts. So let's use now the automatic mesher to see what it will give me. So I select these parts, and there's several types of mesher in NFX. Let's see first what the high-speed tetra mesher will give me. Okay, it gives me something like that. So here I have tetra, and here you see that I have 3 layers of mesh in the thickness. It's not bad. So if you look at the number of elements, I'll have 2870 elements, so you can see it here on the screen. Okay, now let's just go back, so undo, and try the hybrid mesher with the same size. Okay, so here on the contact side it's okay. I have much less elements, so I have to think about is it accurate or not. I could increase a bit the number, but it depends on what I'm interested. Am I interested in the stress in this part? Am I interested in the contact parts? So I will have to mesh more in the area where I have the most of interest. So because as you see here, I have 3 mesh in the thickness, but here I have only 1, so probably in this region it will not be accurate. The thing you see is that for the same mesh size, um, I have 1200 elements, which is much less than what I had if I meshed everything in Tetra. So let's just use that for the purpose of the demonstration, because its only purpose is only to show you how to do. Let's do the same for this part. Okay, and I got also a mesh. Now that I did that, let's do to the next step of this tutorial how to assign the boundary conditions. So in static analysis, and especially nonlinear static, you should be sure that all the possible degree of freedom are constrained. So for example, this part is not moving, so I have to constrain it in several directions. So first of all, you see that in Z direction here and here, it shouldn't be moving in this direction. So I will just choose the constraint, advanced, and then let's choose the faces here and here, and constrain the translation TZ. So the two parts cannot move in Z direction. Now this part is fixed, so I'll just select this plane and this plane, and I just fix that. So I fix the translations. Okay. Now that I did that, I will assign the displacement condition. So displacement condition goes in this part. So displacement face. So I just select the face which will move, and it will move in TX direction of distance of 48 millimeter. Okay. So now I just missed one thing, which is the most important, is the definition of the contact between these two parts. So I have to be more accurate, to use the manual contact, and this is a general type of contact because the two parts are not in contact at the beginning of the analysis, and the master and slave have no importance in this case, so I can switch the two if I use surface to surface contact type. Okay, 5 objects. I can define some contact parameters. So for example, the normal stiffness scaling factor is very useful, especially if my analysis is not converging. It may signify that my contact is too stiff, so in order to increase the convergence, I can decrease this factor, the scaling factor. Of course, there are some drawbacks to do that, because if you decrease the scaling factor, the contact stress in the contact region will be less accurate. So you should know that it's only in order to increase the tolerance, the convergence rate. Okay. I will just use the default parameters. Okay. Now let's check if the contact has been created, manual, and you can see the two faces in contact have been defined. So now I can go into the analysis tab, click on general, just enter a name, and this is a nonlinear static analysis here, nonlinear static, because it doesn't depend on the time. Now click on this and you'll see you'll have the subcase control option. Very important in nonlinear static to set correctly the number of increment and to check this option. So this geometry nonlinear option is to consider the nonlinear geometry due to, so when you have too high stress, the deformation will be nonlinear, and then you have large deformation. So in order to consider that, you have to check this option imperatively. Now, number of increment, very important. If you see your analysis is not converging, you have to increase the number of increments. So sometimes you can have 100 or 200 increments, so it really depends on your analysis. Now, convergence criteria. So now I am doing analysis using displacement. So I will just check displacement and work. Click on OK. And I can just perform the analysis. Okay. Okay, so here I have factorization fail due to the singularity at translation x. So it means that I didn't constrain correctly some of the boundary condition of my model. And this is kind of typical thing that happen if you didn't define correctly the boundary condition. So let's see where I didn't assign correctly. So node, so here you have number of the node 5080 18.3, so 19.3, sorry. So here you have query node element. Let's enter the number. And you see it tells me that I have not, there's a singularity in x direction in here, and this is because I didn't fix this part. So when you are doing a force displacement like that, you have actually to constraint, you have to constrain this face. So it will be pinned. Okay. Now let's edit the analysis case. Click here to be sure that all the boundary conditions are activated, and just try to solve again. Now it seems to be running, so this was the problem. So here you have the advanced in your nonlinear analysis. So here's as I created 20 increments, so the total displacement of 48 millimeter will be divided by 20, and when one of these increment is completed, the analysis will increase. So here now I'm at 10%, and you'll have an output of the maximum stress, the maximum displacement here, so you can check it directly in this text window. So here you have a graphical view of the maximum displacement, and when another increment is computed, the curve will increase, and you'll see the increase like that. If it converges, you will see the word converge, and if it doesn't converge, what the software will do is that it will automatically split the increment in two, because it probably means that your displacement was too large, so it decided to divide the displacement in two steps and then try again. So maybe you'll see it when you have a lot of iterations like that. It's 42, 43. It means that oh, okay, it converged this time, but when it doesn't converge, it just split in two and then it tries again. So nonlinear static is quite time consuming type of analysis, so you always have to think how I can optimize my model to make it with less possible number of elements. If you just mesh it with all very small elements, it will take ages to compute. So you really should think, what is the zone in my model which interests me? where can I reduce the number of elements, where do I need accuracy, and I need to increase the number of elements. So all that is important. So as you see here, as I was telling, it computed 49 increments, iteration, but it didn't converge, so it chose to bisect the increment in two. So now it computed the first bisection and it converged. So now it converted again the second one and it converged again. So now it goes on. So you see the increment here was divided in two, so a point was added in the middle. Now, maybe you're thinking that it takes quite a long time, so you'd like to check what is the result. So, of course, you could stop the analysis and then you will see the result until this step, but you can also directly check the analysis during the computation, so you don't have to wait until the end, and this is very cool. So you have to check open result here, select my analysis case, open, and you'll see the first increment will appear here. So you can click on the different increments. Okay, so first thing, always remember, put deformation to real, otherwise you'll have very strange things. And you can see that it is computing. It computed until here for the moment. So this is displacement and this is the stress. If you want to know maximum and minimum stress, you can check here. Okay. So of course I'll have to wait until a bit until the end. So it takes like around 10 minutes. So I'll just, for the purpose of this, I'll just load a previous analysis that I performed, which is exactly the same. To show you the results. So you have a small slider here that you can drag and drop to view the different increments. So, and now you have the analysis computed. So you can view the displacement and stresses. So you have the stress in the contact region here. So if you're interested to have more types of results, it's possible. You have to right click on the subcase and click on insert analysis result, and here you have, for example, a lot of things. So let me select all to show you all. So you have really a lot of type of result that you can visualize. For example, total SPC force. So here you'll have the force, the reaction of the boundary condition. You have total applied force. So here there's no force applied, only displacement. Okay, so I'll not check that. You have the contact. So you have visualization of the maximum contact. By the way, the legend is in exponential value, but if you want to put it in real value, you have to go here, legend, and there's an option value exponential. Okay, and click on apply, and now you see the value like that. So here you have maximum contact in the model. So if let me check the mesh. So yeah, okay, the mesh is like that. So if you are particularly interested by the stress in this area, I suggest you to do again the meshing and just put more mesh in this stress area, otherwise it would never be accurate. Now let me just show you another method for the meshing because it's important. So I will just delete the mesh that I created. show you how you can mesh it a bit more accurately. So you can use, for example, 2D mesh. Let's choose auto face, for example, and select this face. So you see that I put the seeding, so it will do a small mesh like that. Let's decrease a bit the size. Again, let's say 2. Okay. So here I created nice mesh for this. And now what I'll do is I will just use the extrude option just to extrude this 2D mesh in the selected direction. So okay, I display again the axis, and here I have to input the size. So I guess I don't know what is the size, so let me check. Okay, 3.81. So this is the length, and let's put, let's say, 4 mesh. No, in the other direction, sorry. So okay, I will just do like that. Okay, so now you have this is the preview, and click on OK, and I have generated the mesh. So this mesh is much better than the previous. Of course, it's much more elements, but you see very regular. This is all like quad elements. So I am sure I will get a much better accuracy of the stress in this region with such generated model. So the drawbacks of doing that is that you will not be able to assign the load on the geometry, so the geometrical parts, so I can hide it, and you will have to assign it on the mesh. So when I give you an example, when I assign the constraint, you have the node like that. So I have to just to select the nodes here and fix them, and you see that constraint is assigned to the node directly, not to the geometry face. So assigning loads and boundary to geometry is convenient, but in sometimes it's much better to assign it to the mesh sets directly. And okay, so this is pretty all I can show you for this tutorial. I hope it was helpful for your nonlinear analysis. And if you have any question, you can always send me an email at cyprian@midasIT.com. And well, have a nice day.